We're going to continue our study of radioactivity today. This, I think, technically is still an introduction to radioactivity, and we'll just call it part 2 of an introduction to radioactivity. You will need a new reference table today. That would be Table O. And we'll use Table O to describe things like penetrating power. We'll use it to identify different decay types. And then we'll use a little bit like a combination of algebra and Table O to identify missing particles in nuclear reaction equations. So this is your do now. The part that you would need, I guess you don't need to copy down every single one of these words, but what you could do is you could summarize the question into just its most important parts and then just have an answer. You need to hypothesize about 2 ways that the type of radiation in a smoke detector might be different than the type of radiation in a nuclear bomb. But we'll do that in class, but you do need to copy down the question. And it'll go on a separate piece of paper, and you should put it in classwork in your binder. All right, so here's Table O. Well, this is my excerpt from Table O. Your reference table is in alphabetical order, so it should be after Table N and before Table P. And it looks like this. There's all kinds of different particles on it. You can get lots of different information from this reference table. Not only does it have the name of each of these particles, but it also gives you a notation. And if you know what you're looking for, the notation pieces give you even more information. For instance, this particular piece of the notation is always the mass number if you're looking at an atom, but in this case, we're just going to consider it the mass of the particle. And I think that they sound the same, the things that I just said, mass number and mass, but mass number, definitely is protons and neutrons, and some of these particles don't contain protons and neutrons, yet they still have a mass, so we're just going to call it a mass in this unit. And then down here, we would normally have called it an atomic number, which is equal to the number of protons. But as I just said, not all of these particles have protons and neutrons, so down here at the bottom, we're just going to call this charge. So this is just charge, and this is going to be mass. And then, of course, you get the symbol as well. And then here's a shorthand symbol with just one Greek letter or Roman letter and a charge sometimes, like in the case of this minus and this positive. All right, so you can pause the video, or I'll pause the video, I guess, and I'll write in some information that you should copy down in your notes. All right, so I put in a bit of information that I think that you're going to need. So starting at the top, just in notations, again, as I said, just mass and charge, mass on the top, charge on the bottom, which can help you with the next part in identifying the heaviest particle. The heaviest particle is going to be the alpha, which looks like this little fish swimming to the left. You can see it up here in a nicer font. And the lightest particle is going to be gamma, which looks to me like a fish swimming down a bit, or almost like a Y, but it has a bit of a loop on the bottom. And I say it's the lightest because not only does it have no mass, it has no charge. So we actually consider gammas not to be particles, which is sort of a misnomer on my part because I called it a particle in the question. But we consider it less of a particle and more of just energy, so like a ray, for instance. And I think Table O is wonderful, and you can use it at any time on any quiz or test or anything. But I do think it's helpful to know these masses of these 4 particles and these charges of these 4, just for speed and efficiency, I think is why you would need that. So penetrating power is another interesting concept in chemistry. Not all types of radiation are equally harmful. And we sort of rank their harmfulness based on their ability to penetrate, or, penetrating power. So firstly, a particle must have a lot of energy in order to damage something with which it collides. Now, a particle's energy is usually how fast it's going, but also you can consider its mass as being effective in that as well. And its charge also makes a difference. But I'll just write in energy. So typically, if all the particles get the same initial push from an unstable nucleus, so let's imagine a nucleus that's unstable, it's about to fall apart, and it's pushing its particles out. So they're the particles that are in the nucleus, protons and neutrons and so on, those are about to be ejected from the nucleus. So if they all get that same push, the ones that would move the fastest, or the ones that would have the most energy, would be the ones that were lightest. So moving further, if you order the nuclear particles in order of least to most penetrating power, you're going to consider two things. Firstly, the ones that are lightest and the ones that therefore move the fastest also have the most energy. So they're going to be the ones that are in the running for high penetrating power. But there is another factor, and the other factor is charge. Now, you need to think about two things here. Let's say that you have an atom. So there's my atom, and it has a nucleus, and the nucleus is positive, of course. So I'll put that in, positive. And it has a system of electrons that orbit it, and those are, of course, negative, so I'll add that. My point is that if you are a nuclear particle, let's say that maybe you're an alpha particle or maybe you're a beta particle. And I think the key here is that alphas are positive, and positive 2 actually, and betas are negative, negative 1. If a positive particle were shooting at an atom, it wouldn't have much trouble getting through the electrons, not only because electrons are massless, but because their charge is negative and would not repel the alpha. But by the time the alpha approached a nucleus, it would experience a strong repulsion. You should be thinking about Rutherford's model of the atom right now and the gold foil experiment. So this particle would bounce off of the atom, and it would not be able to penetrate the surface of the material very well. Additionally, beta particles, they're quite light, they're moving very fast, they have a lot of energy, but negative and negative repel. So as soon as it approaches the electron cloud of any of the atoms, it's going to experience repulsion. Therefore, its penetrating power is going to be very low. So if you go back and check table O, and you sort of mentally cross out particles that have a charge at all, and or particles that are heavy, you can easily see that there are just a few particles that have decent penetrating power. I'm gonna ask you to pause the video and take a look at table O and choose a few particles that you think would have good penetrating power based on chargelessness and masslessness, and write them down. Especially if you can do this, try to put them in order of least penetrating power to highest. So here's my list. I think that alphas would be the lowest penetrating power. I think protons, they have a mass and a charge, so their penetrating power is going to be pretty low. If you take a look at betas right here and positrons, I think they're going to have relatively low penetrating power as well because of their charge. They don't have a mass though, so that's an advantage. And then we have the neutron, whose mass is 1 and charge is 0. They have a mass but no charge, so I think they're going to have decent penetrating power because they are not going to be repelled by anything. And then lastly, we have our gammas. The gammas are not going to be repelled, and they're going to be moving super fast. So definitely gamma is the highest, and I would say definitely alpha is the lowest. And try to remember the ones in between, but these extreme ones are extremely important. So when you identify decay types, I think you'll find that it's really, really easy if you're thinking logically. So for instance, when a nucleus emits neutrons, it experiences neutron decay. When an atom loses this particular particle, we would call that alpha decay. I'm going to fill in the answers here. You should pause the video and just make sure that you have an answer for each one of these. They don't have to be in a table. You could just make a list. So here are my answers, and hopefully they all make a great deal of sense to you. Let me know if you have a question in class tomorrow. All right, so here's the part of the lesson that I think is gonna be the biggest takeaway for you, that you're gonna use over and over again all year. It has to do with the law of conservation. The law of conservation is a major unifying law in all of physical science, and it states that matter cannot be created, nor can it be destroyed. It is merely rearranged. We can use this in lots of different ways. But on this slide is going to be probably the first time you've used this particular principle. So I guess just on a really practical level, what this means is that the mass numbers and the charges that we've been looking at on these particles, they have to be the same on the left and on the right-hand side of any particular equation that represents any particular process. So if you take a look at the diagram I've constructed at the bottom of this slide, I haven't given you mass numbers and charges per se, but I did give you protons and neutrons. And on the left-hand side, we have 1 proton and 3 neutrons in this particle. The law of conservation says that after whatever reaction occurs, that you should also have 1 proton and 3 neutrons left. But if you look on the other side of this arrow, what you really see is 1 proton and 1 neutron. So it would seem that we're missing 2 neutrons. So what I'm asking you to put in right here is another particle that contains 2 neutrons. So there's my particle that has 2 neutrons. Okay, so we've reached the pair up. Please copy down this table, bring it in to class tomorrow, and I'm going to add something to the top. It looks like the headers are missing, so pause the video after I have the headers in. And you'll also want to copy down this summary. Both the pair up, the summary, and the do now will go on a separate piece of paper under classwork in your binder.